At a massive construction site on the coast of the Red Sea in Saudi Arabia, heavy machinery is operating non-stop to build a reinforced concrete structure rising straight to a height of 1,000 meters, where wind forces can tear apart and bend even the strongest steel frames. Welcome to Jeddah Tower, the world's tallest building upon completion. To make this superstructure a reality, engineers had to apply a series of unprecedented technological solutions. From handling the foundation's load capacity on hollow coral limestone, designing aerodynamic structures to neutralize wind force, to the technology of pumping liquid concrete hundreds of meters high without changing its chemical properties. So exactly how did engineers build the world's tallest skyscraper at 1,000 meters and surpass physical limits? Let's find out right now, but before we begin, please support us with a like and share this video. Now, let's get started. The Jeddah Tower project is not simply a race for height, it is the heart of a multi-billion-dollar urban master plan called Jeddah Economic City. Saudi Arabia's core goal is to build a global hub for trade, tourism, and technology to reduce the national economy's dependence on oil revenue. To meet the need for massive infrastructure on a limited land area, Jeddah Tower was designed as a vertical city. It will provide hundreds of thousands of square meters of floor space, integrating everything from grade A offices and luxury hotels to high-end residential areas. However, to establish the 1,000-meter milestone in the Red Sea coastal area, engineers faced three extremely fierce physical and environmental challenges. First is corrosion. The coastal environment carries high humidity and salt concentration, directly threatening the lifespan of the steel structures inside the building. Second is aerodynamic pressure. At heights above 600 meters, desert winds constantly change direction and intensity, requiring a design that completely eliminates swaying to ensure safety for users. And third, also the most dangerous boundary, the foundation's geological structure. Beneath the site is a layer of coral limestone. Unlike the solid bedrock found in other megacities, coastal coral limestone is very weak, brittle, and full of natural cavities. Placing a structure weighing over 900,000 tons on this weak ground creates a serious risk of uneven settlement. If the geological problem is not completely solved from the start, every effort to rise into the sky will collapse. To overcome this geological limit, the first technical problem that experts had to solve lay at a depth of over 100 meters underground. Engineers installed a network of 270 giant concrete piles, reaching 105 meters deep. In this brittle and weak coral limestone, they applied the bored pile method, using high-capacity drilling machines to dig cylindrical shafts deep into the ground, lowering steel reinforcement cages, and pouring liquid concrete directly into the holes to form the piles on site. However, a new physical problem appeared. This coastal area has no solid bedrock at deep levels to act as a support point. In normal buildings, the pile tip rests on this hard rock to bear the weight. But at Jeddah Tower, the 270 piles must work on the friction pile principle. The millions of tons of the tower's weight do not push directly on the pile tips, but are gradually neutralized by the friction generated between the rough surface of the concrete and the surrounding soil layers along the 105-meter length of the pile. Nevertheless, the friction principle only works effectively when the surrounding soil is very solid. To handle the numerous natural cavities in the coral limestone, engineers implemented an independent reinforcement technique called high-pressure grouting. Specialized pumps force liquid cement grout deep into the ground. Extreme pressure pushes the grout to fill all cracks and cavities, turning the originally porous ground into a solid block, locking the piles tightly to maximize resistance. Finally, connecting this entire reinforced pile network is a reinforced concrete raft foundation, 5 meters thick, sitting on top. This giant raft foundation acts as a load distribution system. It receives the weight from the core above and distributes it evenly across the pile network, completely eliminating the risk of uneven settlement and ensuring the building remains perfectly stable before rising into the sky. After the raft foundation was completed, the next stage was building the backbone of the entire structure, the central core. Essentially, this is a hollow, reinforced concrete shaft running vertically from the foundation to the very top. This core bears the total static load of the floors and resists twisting forces from external impacts. To build a concrete core rising 1,000 meters, engineers could not use traditional scaffolding for each floor. Instead, they applied self-climbing hydraulic formwork technology. This process took place 24/7 in a closed cycle. First, the tower cranes bring large-diameter steel rebars to the construction site. Here, the team of workers directly weaves and ties these steel bars together, creating a giant and dense steel cage to serve as the structural backbone for one floor. Next, a high-strength steel formwork system closes, tightly covering both the inside and outside of the steel cage. Immediately after, high-capacity pumps push the liquid concrete mixture into the formwork, filling every gap between the steel bars to cast the solid concrete core wall. Finally, and the breakthrough of this technology, is the hydraulic sliding process. The entire system of formwork, safety scaffolding, and worker platforms is linked as a single unit, connected to the support base by heavy-duty hydraulic jacks. As soon as the poured concrete reaches standard hardness, the hydraulic system automatically pushes this entire massive assembly up to a new floor. This cycle of weaving steel, pouring concrete, and hydraulic sliding repeats continuously. As a result, the central core is always the highest structure on site, rising into the sky at an average speed of one floor every few days. Only when the concrete core is solid do the steel beams, floors, and exterior glass start to be assembled on the lower floors below. As the central core rises into the sky and passes the 500-meter mark, engineers face the most destructive physical force for superstructures: atmospheric wind pressure. At this height, high-speed winds hitting the building's surface are torn apart, creating vortex shedding behind the structure. This is known as the Karman vortex effect. If these vortices reach resonance with the tower's natural vibration frequency, they create a powerful sideways force, causing violent swaying that could break the steel-reinforced structure. To neutralize this resonance, engineers do not install mechanical counterweights inside the building. Instead, they turn the very exterior design of Jeddah Tower into a giant aerodynamic machine, simultaneously applying two core design solutions from the ground to the top. The first foundational solution is the Y-shaped floor plan. This three-wing structure was cast as a single, solid block from the raft foundation and extends into the sky. It was calculated at precise angles to ensure that, no matter which direction the wind blows, there is always at least one wing acting as the direct compression-bearing part, while the other two wings act as anchors to disperse the tension force. This geometric distribution creates a permanent state of balance for the structure. However, the Y shape only solves the direction of the force. To break the frequency of the wind, engineers apply the second solution directly onto these three wings: an asymmetrical, tapered setback design. Starting from the middle floors upward, the horizontal surface of the building continuously narrows. The key point is that the three wings do not taper equally. They are designed to end at three completely different heights. This height and taper asymmetry breaks the structure of the airflow. As the wind-resisting surface changes continuously along the vertical axis, the generated aerodynamic vortices will have completely different sizes and speeds. Consequently, they cannot synchronize to form a unified vortex band along the tower. Without synchronized resonance, the horizontal swaying force is completely neutralized, allowing the building to remain perfectly still despite standing in heavy desert winds at 1,000 meters. Another interesting aspect of this structure is the material used to cast it. The concrete used here is high-performance concrete mixed with ultra-fine microsilica particles. This mixture creates absolute density, and combined with superplasticizer additives, it slides smoothly through double-walled pipes under the pressure of ultra-high-capacity hydraulic pumps. Furthermore, to combat the 50 degrees Celsius desert heat, engineers use tons of flake ice to mix the material instead of liquid water. The slowly melting ice flakes dissipate the heat generated by friction, keeping the concrete batch consistently cool below 28 degrees Celsius until it reaches the top of the tower. And as the concrete core axis rises, the independent exterior glass facade system is installed closely behind. The flexible joint design allows the entire glass surface to freely slide slightly, both absorbing forces when the building sways and reflecting the harsh desert heat. Enduring a historic 7-year freeze exposed amid sandstorms, the entire foundation and concrete core of Jeddah Tower still stand firmly, passing the most brutal quality test. Now, as the cranes resume operation, this mega project continues its journey to bend physical limits, to establish the world's first 1,000-meter milestone. How do you evaluate the design and engineering of this structure? Please leave your opinions in the comments section. If you found this video helpful, don't forget to like, subscribe to the channel, and turn on the notification bell to join us in dissecting the next giant projects. Thank you for watching. Goodbye, and see you next time.